My dear students, in the last semester, you have known the knowledge of difference in the chapter of the differential calculus, where we are all known about the expansion of a differential function f of x in an infinite series. Likewise, the Taylor series expansion of f of x about x equal to a is an infinite series in the increasing powers of x minus a. Similarly, the Maclaurin series is an infinite series in increasing powers of x. Okay, we have solved so many examples of this type in the last semester. And now, in many engineering problems, it becomes necessary to expand a given function f of x in a series containing sine and cosine terms only, which belongs to a class of functions called periodic functions. This is our new syllabus which we have to discuss in the present semester. Now we have observed the word periodic function. What is a periodic function? Let me go for the definition. As you might have already known this definition in the PUC second year. Okay, let it be. We shall discuss it once again. The definition will be a real valued function f of x is said to be periodic function of period capital T if f of x plus t is equal to f of x. This means what? When the given function and the given angle is replaced by that angle plus some constant term which gives the same function, it is called periodic function. Observe the definition shown here. For example, sin x and cosines are periodic functions of a period 2 pi. 2 pi means what? T is equal to 2 pi. How it is? We know that sin of 2 pi plus x equal to sin x, cos of 2 pi plus x equal to cos x using the 4 quadrants formula. Okay, now we shall go for the trigonometric series and Euler's formula. The function k, I mean the constant cos x and sin x, where n equals to 1, 2, 3 and so on up to infinite, are all periodic functions of a period 2 pi. As we suppose if we consider the constant k is equal to a naught by 2, then the relation of the form, observe the relation here, a naught by 2 plus summation n is equal to 1 to infinity a n cos n x plus summation n is equal to 1 to infinity b n sin n x, where a naught, a n and b n equals to 1, 2, 3 and so on are all constants is called a trigonometric series. After getting the values of a naught, a n and b n, these are known as the constant values. How it is possible? We shall see it now. Hence a naught equals to 1 upon pi integration between c to c plus 2 pi f of x dx. n is equal to 1 upon 2 pi c to c plus 2 pi f of x cos nx dx, and bn equals to 1 upon pi integration between c to c plus 2 pi f of x sin nx are called the Euler's formula. And for this purpose, we have to know the Bernoulli's form of the integration. What do you mean by Bernoulli's form of integration? While doing the examples under the integration for the product tool, we have known the integration by parts. The same rule is applicable here. What is that? Integration of uv dx equal to what? Let me call it by u into v1 minus u dash into v2 plus u double dash into v3 minus u triple dash into v4 and so on. Here v1 is the integration of v, v2 is the integration of v1, v3 is the integration of v2, v4 is the integration of v3 and so on. Here dash represent the respective derivative. U is the given function, u dash is the first derivative, u double dash is the second derivative, u triple dash is the third derivative and so on. And the process will be continued till u attains its constant term. It's a constant term. I will repeating the word constant term. Okay, for this purpose we shall have some two examples. I am not giving to give the proof here because you might already know these two results. Integration of e to the power x cos bx dx equal to e to the power x upon a square plus b square into a cos bx plus b sin bx. Integration of e to the power x sin nx dx equal to e to the power x upon a square plus bx b square plus b square into a sin bx minus b cos bx, where sin n pi is always 0 for any integer, cos n pi equal to minus 1 raised to n, where n equal to 1 where n is even is equal to minus 1 when n is odd. Okay. Now we shall discuss about one example. Obtain the Fourier series of f of x equal to pi minus x upon 2 in the interval 0 to 2 pi. As you might already known, c to c plus 2 pi. The interval is given by here 0 to 2 pi. C means what here? 0. C plus 2 pi means what? 2 pi. The Fourier series of f of x with period 2 pi. How to get the period here? Take the end point of the interval 2 pi minus take the initial point of the interval 0. this will become what? 2 pi minus 0 will be 2 pi. This is the period of the given function. Where f of x equal to a naught by 2, summation n is equal to 1 to infinity a n cos nx plus summation n is equal to 1 to infinity b n sin nx. Where a naught is given by 1 upon pi, the integration between 0 to 2 pi. How it is 0 to 2 pi? It is already shown here. It is given. F of x dx and a n is equal to 1 upon pi between 0 to 2 pi f of x cos nx dx and bn equals to 1 upon pi c to c plus 2 pi. It is 0 to 2 pi f of x sin nx dx, where a naught equals to 1 upon pi between 0 to 2 pi minus x upon 2 dx. The integration, after getting the integration and so on, the result reduces to 0. Therefore a naught is 0. Now come to an. It is again 1 upon pi c to c plus 2 pi minus x upon 2 cos nx. Here this interval is, again we shall replace it by 0 to 2 pi because the particular integral is given here. By the Bernoulli's form of the integration, as you already known, this will become this 2 will go outside being a constant term, keeping 1 upon 2 pi outside, pi minus x u into v1 minus u dash into v2. Just observe here, u means what? Pi minus x. v1 is what? Integration of cos nx. What is the integration of cos nx? Sin nx upon n. Minus, there is a minus sign between these two results. And this is u dash. U dash is what? Pi minus x. This is what? Minus into integration of sin nx upon n, that is v2. It will become minus cos nx upon n square. The interval is between 0 to 2 pi. And after, because we know that sin n pi is already 0 and cos n pi equal to minus 1 raised to n, and this will become, after simplification, minus 1 upon 2 n pi, because the first condition is already 0 and only taking the second term here, 1 upon 2 minus 1 upon 2 pi n square minus 1 upon 2 pi n square cos n pi between 0 to 2 pi, hence sin 2 n pi is 0, it is 0. Therefore an is equal to 0. Now come to bn. bn is equal to what? 1 upon 2 pi between 0 to 2 pi minus x upon 2 sin nx dx. Again using the same Bernoulli's form of the integration, u into v1 minus u dash into v2. Here u is equal to pi minus x upon 2 and v is equal to sin nx upon sin nx with respect to x. Therefore u is pi minus x, v1 is integration of sin nx is what? Minus cos nx upon n minus integration of pi minus x, it will be minus into integration of minus cos nx upon n, it will become minus sin nx upon n square. Interval is between 0 to 2 pi. After simplification, bn will be reduced as to 1 upon pi. The results are, the details are already shown here. Just go for doing the calculation. You can find the result. Bn is equal to 1 upon n. Hence f of x becomes x square, that is putting the a naught, an and 0. A naught is equal to what? Pi square by 3. An is equal to 0. Bn will be, it is already, come to here, putting all the values of a naught, an and bn, f of x will be pi minus x upon 2. What is the condition we have got? We have got here a naught equals to 0, an is equal to 0. Therefore bn is only the non-zero term, and hence putting the value of bn in the result number 1, summation n is equal to 1 to infinity 1 upon n sin nx dx. Therefore, my dear students, before going to solve the examples on the Fourier series, please take care about the integration by parts. This is the only important thing of the given example for any given interval. Okay, thank you.